My last class, I discussed about few criteria for a polynomial fx belongs to some polynomial ring, few criteria for which this to be irreducible. So that is very important, whether an element. So before that, I have already discussed about prime elements, irreducible elements, and so on. So in case of a polynomial ring, the elements are basically the polynomials, and why these polynomials are playing an important role, that today I will try to show that why these irreducible polynomials are very important. So irreducible elements are important, of course, for a ring, but for a particular ring, here this polynomial ring is a particular ring, and for that particular ring, why the polynomials are important as irreducible elements. That's very important. So today again I am going to discuss about few things which will be very useful from competitive exams viewpoint. Okay. So the first thing is that first we'll go for Euclidean domain. Euclidean domain. So as usual, since domain is there, that means Euclidean domain must be an integral domain. But before going to the basic definition of Euclidean domain, let us first try to have a look at the divisions. So we all know that in integers we can do divisions. For example, if I take any two integers, for example, say a equal to 7 and say b equal to 5, and if I ask you, can you divide 5 or can you divide 7 by 5? So you are going to divide 7 by 5. So what would be the quotient? The quotient will be, of course, 1, and here 2 is the remainder. That means if we take any two elements from Z with, of course, B not equal to 0, then you can have a division. Like you can always divide A by B. So the confidence that we already have within the ring Z plus dot. Okay. So we all know what do we mean by division. Now, if I ask you this simple question that can you divide minus 7 by 5? Can you divide minus 7 by 5? Then what would be my quotient and what would be my remainder? Quickly, can anybody tell me what would be my quotient and what could be my remainder? Sorry, I couldn't get your voice. Uh, could you?
Minus 2 and 3.
So it is minus 2. Somebody says this is minus 2 and this is 3. Any other answer? Anybody? Anybody? So somebody says any other answer? Okay. So I'm sure that many of you, though they are very confident about division, but when I ask you this question, you'll be a little bit confused. And then you will get different answers. So yes, the answer is correct. So this is minus 2. That means if I do like this, then it would be minus 10. And when I will do this plus, that means this is 3. So the remainder is 3 and the quotient is minus 2. But many of the people, they also do like this. So minus 7, they get little bit confused and they do it, say, for example, this is nearest to this, maybe say minus 1, and then they will get minus 5, and then this is plus minus 2. So they get like quotient is minus 1 and remainder is minus 3. Okay, so why this is so? So minus 7 could be written as minus 1 into 5 plus minus 2. Here also we can write minus 7 equal to minus 2 into 5 plus 3. So both the expressions are like this, q into, say, it was my b, so it was my a, plus remainder. So here also A equal to Q into B plus remainder. So both the expressions looks almost same, but why I say that this is of course wrong and this is correct. So what is the difference between these two? Both of them can be written exactly in the same way, like A equal to QB plus R. Here also I'll get A equal to QB plus R. But I say that this expression is wrong, but this expression is correct. So what is the basic justification for that? So though we use very frequently this kind of divisions, we must remember the division algorithm. What it says in case of integers, what it says, so division algorithm. It says that let A and B be two integers with B not equal to 0, with which you want to divide. Then there exists Q and R belongs to Z such that A can be written as QR, sorry, QB plus R, where this part is very important, where 0 is less than equal to R is strictly less than mod of B. Sometimes we forget about mod of B. That's why the confusion comes. If you are fixed here, so we all know that the remainder should be greater than equal to 0, but it has to be, most of the cases we assume that this B is strictly less than B, but that is wrong, because if B is negative, then in that case you will be 0 less than equal to or less than some negative integer, which is absurd. That's why to make it unique and to make it proper and justifiable, we have to put this B to be mod B, and that is the absolute correct statement. That's why you will not have any kind of confusion while doing with this. So here what I see that here R is minus 2, and of course then 0 less than equal to R less than mod of B, which is not true. So here the remainder is less than 0, but in our case the remainder will always be strictly or greater than equal to 0, and it has to be strictly less than mod of B. That's why if you do this thing, then suddenly your answer will be fixed, and that answer will be this. So this is the division algorithm, and this division algorithm can be generalized further, and that's the idea for Euclidean domain. But before going into that, let us try to divide. Suppose I consider two polynomials, fx equal to say x plus 1, say x square plus 1, and say gx equal to say x cube 3x cube plus 2x plus 1. Now can you divide can you divide gx by fx? What will be your answer? In, so the question is where? In zx. Can you divide this?
No, actually the degree is greater than, so I can't divide.
You cannot divide gx by fx. Okay, let's see. So
GX
here,
by, oh, okay, okay. I thought the converse. That's why I said it. X square
okay,
plus
so
1. Yeah, I can do it.
okay. Next, my second question: can you divide fx by gx in zx? Now, what will be your answer? So here you say that yes, you can do, and here you say that no, you cannot do, right?
Yes, sir.
Because the degree is greater. Okay, okay. Uh, Let us try to have this. First of all, here fx is this and gx is this. So how can I divide this? So the same division algorithm that we usually follow. 2x plus 1. So here I put 3x, then it becomes 3x square plus 3x, and then that will give me, so this will be minus, and that will be
Okay.
minus x plus 1. So my quotient will be, this will be my q, and this will be my remainder. Okay. So
Sir,
here,
that's 3x cube.
sorry. Okay, this 3x cube. Yes. Thank you. Yeah. So that's gone. Yeah, the quotient and the remainder will be the same. Okay. So here we can divide it. So the question is, can we divide, can, okay, can this be? Now my fx is, say, 4x, 4x square plus 4, and my gx is same, 3x cube plus 2x plus 1. And I want to find, question, can you divide, can you divide gx by fx? Now what will be your answer? Can you divide gx by fx?
Sir, in where? ZX or QX?
In zx, of course, all the things in zx.
Okay.
So again, if you try to solve the same problem like this using the similar technique, so here you had 4, and here you had 3x plus 3x cube plus 2x plus 1. Then the first problem that you will face is how to resolve this part. So here what we did, I just made 3x multiplied with this so that the highest degree term will get vanished, right? So that after multiplying this with x squared, it becomes 3x x cube, and that's why both of them are same. As a result, you can just ignore them or you just reduce them. But here, what you can multiply, so you have to multiply to have this 3x cube. To get this, you have to multiply this by 3 by 4x, right? But understand, try to understand that this 3 by 4 is not within z. As a result, these things cannot be from, this thing cannot be from zx. As a result, you are facing some problem while dividing this polynomial, by this polynomial here. So unlike z, where the only criteria was b should be non-zero, here you can see that if we consider this to be b, this b is a non-zero polynomial, but still we are unable to divide this by this b. That means the polynomial ring zx has some specific property that not every non-zero polynomial will be able to divide any other polynomial. So that's a interesting point, and that we have to consider. So that's the idea of Euclidean domain. So we consider an domain, an integral domain in which the division is possible. So division for arbitrary ring is quite clear to all of you. Now let us try to define what do you mean by Euclidean algorithm in general. So Euclidean domain. So first of all, it has to be a domain, that means an integral domain. So an integral domain E is said to be an Euclidean domain if there exists a function. Now I will explain what do you mean by that. There exists a function u from non-zero elements from all non-zero elements of the Euclidean domain into the set natural number union 0. Mind that many of the authors, they consider n to be the set of all natural numbers starting from 1, 2, 3 and so on, and many authors consider n to be starting from 0. So in my notation I will consider n to be starting from 1, 2, 3, and that's why I just include 0 here. If there exists a function u satisfying the following properties. So what are these properties? First of all, you will be able to have the division algorithm property. So first property is, for any two elements, elements A, B belongs to E with B not equal to 0, there exists QR belongs to E such that A equal to BQ plus R. Now the second part is interesting, where, so try to remember what happened for Z. In case of integer, what we have, what we should write here, the remainder should be strictly less than equal, sorry, less than equal to 0, less than mod of B. Now the question is how to explain the whole thing in terms of arbitrary integral domain. So here E is my arbitrary integral domain, and there, here, this usually, this notations we usually use for Z. So the question is, how do I have a kind of similar concepts here? That's why, for to have the similar concept in case of Z, here we consider this U function. So U is called the valuation function of the Euclidean domain. So here you understand that in case of Z, I will have the U function as U minus 0 to the set of all natural numbers union 0 satisfying. So in case of U is defined to be U of some x is nothing but mod of x. Okay. So that's my U in case of Z. So how do I define here? So where either R equal to 0 or valuation of R should be strictly less than, sorry, it has to be strictly less than valuation of B. So have a look at this. This is, I have made it in two parts. One is R equal to 0, or if R not equal to 0, you can see that the valuation is only defined for non-zero elements of E. That's why if R equal to 0, then you cannot apply the valuation function on E. Okay. So in this case, that means, or means if R not equal to 0, then you can apply valuation of R. That valuation of R must be strictly less than the valuation of B. That is important. Now you just try to think about Z. So here in terms of Z, we can write either R equal to 0 or valuation of R should be strictly less than valuation of B. In other way, what is that valuation? I just explained that valuation is nothing but mod. That means mod of R should be strictly less than mod of B. Okay. Now, in case of here, since we are merging both of them, that's why it can be written in a similar way in one condition. Okay. That's why the remainder is always less than this and greater than this. So is it clear to all of you? So the valuation should be strictly less than the valuation of B, and this 0 here I have, in case of Z, I have already given R equal to 0 or like this, and that can be explained, or that can be distributed like this. So that's the first property that we need to do. So you can understand that this property is nothing but a generalization of the properties of Z that usually we have. Now the second property is that, so some of the authors, they remove this property. It says that in general, what happened in case of integers, always we have this is less than equal to order of AB, right? So mod of AB is less than equal to mod of A into B. So that's important property that many of the authors, they also include this property for all AB belongs to E minus 0, valuation of A is less than equal to valuation of AB. That means if you make the product of any two non-zero elements, that valuation should be greater than equal to valuation of only one element. Okay, so that's the extension of this definition into Euclidean domain, and that is true for any arbitrary integral domain. So an integral domain satisfying these two properties is said to be an Euclidean domain. Okay, so what is this? Basically, this is nothing but the extension of your division algorithm for Z. What we had for Z, that is actually extended into arbitrary integral domain. So that's the basic idea for this definition. Okay, so let us try to have some few examples. So few examples if you consider. So examples, so of course Z plus dot is an Euclidean domain, is a Euclidean domain with, so what is important here, with valuation of A is defined as mod of A for all A belongs to Z minus 0, right? Now tell me any other example. So let F be a field. What's about Fx? Then Fx is a Euclidean domain. So now can anybody be able to tell me what would be the valuation of this? What would be the valuation of this? So what would be the valuation of this? So this is my first example. Second example is, let F be a field, then Fx is a Euclidean domain. So to prove this, this is an Euclidean domain, what we need to do? We need to find some valuation, proper valuation. So on which we are giving the valuation? On a polynomial. So
Sir,
Maybe
with,
degree.
degree of the
yes,
polynomial.
very good. So the degree of the polynomial Fx. So if you define like this, then you can very easily prove that Fx is an Euclidean domain. So that is very easy. So first of all, F is a field. That's why Fx is an integral domain. You cannot have zero divisor within Fx. So since F is a commutative ring with 1, Fx will also be a commutative ring with 1. F does not have any zero divisor. As a result, Fx will also not have any zero divisor. So the first step is done. That is, Fx is an integral domain. Now what we need to check? We need to check there exists some valuation function. For example, here there is a valuation function. So you need to prove that this is really a valuation function, and proving that is not very difficult. If you stuck somewhere, you just Google it and then you will find plenty of such examples or plenty of ways to do so. So it's very easy. Now third very trivial example could be, let F be a field, then F is an Euclidean domain, is a Euclidean domain. So what would be your valuation function? v of some element, non-zero element of f, what would be the valuation function? Can anybody be tell me?
1.
Very good. It's 1. If you consider VA to be 1 for all A belongs to F minus 0, then you can very easily prove that uh, this field is a valuation function. Now my question is, these questions are quite interesting. Question is, let E be a Euclidean domain. So can this valuation function be unique? So can you have can you have two or more two or more valuation functions on E, valuation functions on E? That means is this valuation function E, sorry, U is fixed with respect to this E? Can you have two or more valuation functions on E? What will be your answer? Is this unique, or you can have more than one valuation function on the same E? So since E is an Euclidean domain, it will have at least one V. Now the question is, can you have more than one such valuation functions?
Sir, I think this is not unique.
Okay, then can you give some example?
Take anything. If I plus any uh, any positive quantity, then that will be also the valuation function, I think.
So can you give me some specific example, some specific
Like,
E and then two V, two U
if I
something.
define fx to f degree of polynomial plus 1, will it make any difference?
Okay, so you defined valuation from fx to f, fx minus 0 to natural number. I mean, natural number 0 means natural number union 0, defined by fx equal to degree of fx plus 1. Okay, so he has given some example. Now check, if so already you have seen that if we have only degree of f, then that would be a valuation function. That means that will give me the Euclidean domain. But if we have this, then will that be again be satisfied or not? That you need to check. Okay, so I will give you the answer. The answer is you can have more than one valuation functions on some specific ring. So what you need to do, you need to find some examples. So the answer is the valuation function may not be unique. Okay, and he has already given one example. Now it's your turn to check whether that is really a valuation function or not. So another example could be Z I, that means the Gaussian ring. So A plus IB such that A and B belongs to Z. Question is it a Euclidean domain? And if so, then what would be the valuation function? Can anybody tell me what would be the valuation function?
Sir, A square plus B square.
Okay, so valuation of A plus IB says A square plus B square. And you can check. So this check, this is a homework. So you must check this. If you are unable to do so, you just Google it and then you will find this result. This is quite interesting. There are plenty of different kinds of proofs. Some geometric proofs are there using this lattice point and all. You can check this, and then you will able to see that how this can be proved. So of course this is an Euclidean domain, this is true, and the valuation function, if you define like this, then this could be an Euclidean domain. Now if I just make a simple twist of this, if I have root 3i, Will this be an Euclidean domain? Will this be an Euclidean domain? So with respect to say, so you need to have the valuation function. So here the elements will look like uh, root 3IB. So what would be your valuation function? Your expectation would be, what should be the valuation function?
Maybe modulus of that number.
Hmm? Sorry?
Maybe modulus of that number.
So what
Modulus
is,
of that number.
okay, what is that?
A square plus 3, a square plus 3b square.
Okay, somebody says a square plus 3b square. Now try to check whether with respect to this is also a homework. With respect to this, whether this is a Euclidean domain or not. Okay, so they are very interesting. So what we have already seen is that if f is a field, then fx is an Euclidean domain with respect to this degree and all. Now we will move little forward. So this theorem is also very important, and many of the times this comes as an question in any of some of the competitive exam. That is, every uh, PID, every Euclidean domain is PID. So in our last class, we have already talked about what is PID. That means an integral domain in which every ideal is generated by single element, that is known as PID. And it says that every Euclidean domain is a PID. The proof is not very difficult. So what I just give you the kind of hints of this proof, and then you need to check it. The proof goes like this. So let E be an Euclidean domain, E be an Euclidean domain, then it must have some valuation function. Let V from E minus 0 to natural number union 0 be its valuation function. So what you need to prove actually? You need to prove that E is a PID. That means you need to take any arbitrary ideal of E. If that is generated by a single element, then you are basically done, right? That you have to prove. Okay. So let I be an ideal of E. So if I is an zero ideal, then we are done basically. Then I is generated by 0. So we are done. So assume that I is non-zero. Then there must exist some non-zero element. Then let A not equal to 0 belongs to I. Okay. Now I am going to consider a set. So what I need to show that this I is generated by some single element. That's all. So now I consider a set, say all such valuation x such that x is a non-zero element of I. So belongs to I. Okay. So this is a subset of whose subset is this? This is a subset of whose subset is this? So collection of all valuations of non-zero elements of I. Then whose subset is this? This is a subset of course, natural number union 0. Is this subset a non-empty subset or it's an empty subset? How will you prove that this is a non-empty subset of this? How will you prove that this is a non-empty subset of this? Because already A is there. So A is non-zero element. So of course VA, as VA belongs to this set Vx such that x not equal to 0 belongs to I. So this set is non-empty, and this is a non-empty subset of n union 0. Then by well ordering principle, what you can say? Can anybody be able to tell me? Then by well ordering principle, what can I say?
So there is an element of least order.
So there exists an element which is least with respect to this ordering, right? And that list element will help you to generate the ideal I. So that's the proof. So that proof is easy now. Now I think you will be able to prove. Any guess? Anybody? Can somebody be able to give me any clue how to proceed then? So then by well ordering principle, this Vx such that x not equal to 0 belongs to I will have a least element. Say what is that? Say V of L. Okay, what does it mean? Then if you have any element from here, then VL will be the least. That means VL will be less than equal to V of X for all non-zero, less than equal to for all non-zero element belongs to I, and so on. Now this VL will help you. So this L will certainly help you to have your ideal generated by L, and so on. So now I think you can do it. You can read this result from any of the textbooks, and then you will get this idea that that this I is basically generated by L, and this the result will be proved from here. And I think it's not very difficult, because you will have to give the idea that this is the least element of this set, and then that will be done. Okay, so I'm not going to give you the proof of this, but I am actually doing these things because I need these results, but I'm not giving you the proof because I don't have that much time to do so, because I want to do few of the problems. That's why. So what is that result? It says that the result, it says that theorem, every Euclidean domain is a PID. Okay, so that's the result. Now I'm going to give you very important result. That result says that let F be a field. Okay, then let's see. Let's not F be a field. Okay, let's start with uh, this way. Maybe let F be a commutative ring with 1, then the following are equivalent. What is that? 1, F is a field. 2, Fx is a Euclidean domain. And third one, Fx is a PID. So this is if and only if conditions. All of them are equivalent. So 1 implies 2. F is a field, then Fx is an Euclidean domain with respect to degree of the non-zero polynomial we have already seen. If Fx is an Euclidean domain, we have seen the more general result that if it is an Euclidean domain, then it has to be a PID. So fx is an Euclidean domain, then it has to be a PID. So it's a particular result. So only thing that is left with is if fx is a PID, then f is a field. So start with some. Uh, so what you need to show that you have already assumed that fx is a PID, and then from there you need to check that f is a field. Since fx is a PID, then of course fx is an integral domain. That means fx is a commutative ring with 1. That means f is also a commutative ring with 1. So what you need to show that take any non-zero element from f. What you need to show that f inverse exists. That's all. If that means there exists some element C or B belongs to R such that A into B should be equal to 1. That's all. And that proof is also very straightforward proof. I'm not going to give you the details of that proof because I want some problem to be solved in this class. Okay. So this is also very important result from competitive exams viewpoint. And I request all of you to have a look at these results because they are very important. These proofs are very important for normal exam, but the result is very strong result in solving many of the important problems. Okay. So now the question is, what is the relation between, so till now we have already defined the Euclidean domain, then I have already defined, so if f is a field, then that certainly that is Euclidean domain, and if it is an Euclidean domain, then certainly that will PID. Now, can we go little further? So in our last class, we talked about unique factorization domain. We talked about factorization domain and all. So it can also be proved that every PID is a UFD, and every UFD is of course a factorization domain, and every factorization domain is an integral domain, and every integral domain is a commutative ring with 1. Okay. So this result is very, very important from any competitive viewpoint, competitive exam viewpoint. You need to remember this result. I am not going to, I have already shown you up to this, but you can also prove this. They are not very difficult. And if it is an unique factorization domain, then certainly this will be a factorization domain. And since D is there, ID is also there. So you need to prove that every, so this part I'm not going to give you the proof, but take any of the books, then you will find this result. That is every PID is UFT. So you may read my book or Malikshan Moroshan book or even Damit Food book, then you will find this. So this is also your homework. Okay. But interestingly, all the converse part are false. That means you can find an Euclidean domain which is not a field. You can find a PID which is not an, so all the other directions are false. So many of the examples are trivial examples, and few of the examples are really tricky, and few of them are really out of our scope. So I request you to Google it to check what would be the converse one and what would be the counter examples. For interviews, these counter examples are very important. For example, give me an example of a UFD which is not a PID. Okay, can you quickly give me an example of a UFD which is not a PID? Anybody?
Sir, ZX.
Very good. So consider ZX. Consider ZX. Just now we have seen in this result that if f is a field, then all the things are equivalent. Okay, so if F is a field, then Fx is a Euclidean domain, Fx is a PID. It's very important result. Many of the questions could be solved by using this, just simple this result. So if I consider Zx, and you can understand that since Z is not a field, Zx can never be PID. Okay, but Zx is a unique factorization domain. So why it is unique factorization domain? Can anybody be able to tell me why it is unique factorization domain? You can give some example, but proving that it's a UFD, it would be difficult. It satisfies few of these properties that requires few of the proofs, similar to the proof how PID implies UFD and things that one can study formally, but intuitively for competitive exams, you can understand that for every polynomial over Z, you can have unique factorization in terms of product of irreducible elements. That's why this is UFD. But proving this formally may not be that easy. Direct proof may not be that easy that, okay, this factorization is unique. Anyway, so that's a good example that ZX is an example of a PID, which is an which is not a sorry is an UFD which is not a PID. So it's a UFD which is not a PID. Again, if I consider Rx, this is both PID, and once it is PID, then this arrow will follow. That is, it will be UFD. This is also uh, FD integral domain and so on. And as this is a field, this part is also true. So PID, in case of a field, this result shows that if it is a field, then it must be an Euclidean domain as well as a PID, and it is if and only if. So if it is a field, then this both way relation is satisfied, and so on. So this is quite interesting, an example of a factorization domain which is not a unique factorization domain. That's quite important, quite interesting. Uh, so you just need to check. So also this is also very interesting example of an integral domain which is not a factorization domain. That means not every non-zero non-unit element could be factored with respect to finite number of irreducible elements. So that these tools are quite interesting. So you just Google it and you will get all the detailed results. Okay, now let us directly come to a few of the interesting problems that we have. Okay, it came in December 2014. Can you please tell me what would be the answer? It would be multiple correct choice. That means you might have more than one solutions. Can anybody tell me what would be the solution for that? Which one? 1, 2, 3, 4, or any combination of 1, 2, 3, 4? Okay, Orko Provo.
Yes, sir.
Okay, please tell me. So Rx be the polynomial ring over R in one variable, and I be an ideal of Rx. Then I is a maximal ideal if and only if I is a non-zero prime ideal. Is it true or false? Is it true or false?
Sir, true.
Why?
Sir, Rx is a PID,
Yes.
and
So
every non-zero prime ideal is maximum.
very good. Okay. So second one will answer. Bonusri. Bonusri, are you there? Okay, it's Bhaskar. So Bhaskar,
স্যার ভাবছি একটু এটা
so I is a maximal ideal if and only if the quotient ring I quotient Rx quotient I is isomorphic to R.
স্যার 2 হবে
Why? Yes, you are right. Why? You are right or wrong? That's my question. Okay, anybody? You may not be right. So, anybody? Anybody else? Okay, anybody else? So, do you remember? Okay, Nikita. So, if I is a maximal ideal, then the quotient is
False.
isomorphic to false. Why? In my class, I have already did the same thing. Okay, let me give you some hints.
Sir, if we take the ideal to be ideal generated by x square plus 1,
Very good.
then it is a maximal ideal, but isomorphic to C. Yes.
Exactly. So this is a maximal ideal, and we in our class we have already seen that Rx quotient x square plus 1 ideal generated by is isomorphic to C. So it's not C is not isomorphic to R. Why C is not isomorphic to R? Can anybody tell me why C is not isomorphic to R?
Sir, in C, there is a element I whose order is 4, but in R we can't find such element.
Very good. So that's why they are not isomorphic, and as a result, the answer is false here. Very good. Okay, what's about this? I is a maximal ideal if and only if I is generated by x, where f is a non-zero, non-constant, irreducible polynomial over R. Is it true?
Yes, sir. True.
True. Very good. And what's about the last one? 4. Last one.
Sir, true.
Sir, true. Also true.
Because any polynomial of degree 3 or more is reducible in Rx.
Yes. I is a maximal ideal if and only if there exists a non-constant polynomial fx belongs to I of degree less than equal to 2. So, according to you, this is correct. Any explanation except from Orco Provo? Anybody else?
Sir, if fx has no root in R, then it is true.
If fx has no root in R, okay. Uh, I is a maximal ideal if and only if there exists a non-constant polynomial fx belongs to I of degree less than equal to 2. So, according to Orco Provo, it's correct.
Sir, that fx has to be irreducible. So it cannot
Sir,
have any.
sorry, sir. Wait, x
Yes, sir.
minus 1 whole square, that's a counter example.
So it cannot
So,
have any roots in R.
so what would be your? It cannot be if and only if, right?
Yes, sir. It cannot
Yes.
be.
So 4 is also false. Is it clear to all of you? So as Orko mentioned, so it's an if and only if result. Suppose there exists a non-constant polynomial of degree 2. Suppose x minus 2 whole square. So do you think that the ideal generated by x minus 2 whole square is a maximal ideal in Rx? It's not, of course. So the result is false. So the actual answer will be the first one is correct. The third one is also correct. So first and third will be the answer. Is it clear to all of you? Is it clear? Okay. Then let's come to this problem. It came in December 2013. Let fx equal to this, then which of these options will be correct? It might be also a multiple correct choice answer. So you might have more than one answer correct. Tell me which one will be the correct option. So it's fx equal to x cube plus 2x square plus x minus 1. Determine which of the following cases f is irreducible over the field K. Okay, if it is from Q, what will be your conclusion? So you need to check whether the roots are within Q or not. But from this equation, it's not very easy to understand whether the roots are within this or not. So you may try with F2 first, the K equal to F2. That means Z2. Then that may be easier for you to think. So if you consider with respect to F2, then what would be your polynomial? The polynomial should look like, how the polynomial should look like? The polynomial should look like, the polynomial was fx equal to, can anybody tell me, x cube plus 2x square, x cube plus 2x square, then plus x minus 1. It was right. Yes, x plus 1. So if I consider f bar x in z2x, then how the polynomial will look like? The polynomial will look like x cube plus x plus 1. So plus minus 1 is same in z2, like this. Now can anybody tell me whether this is irreducible or not? So if you put, how to check this? I can put only two elements. So try to find what is this value 0 and try to find what this value 1. So if you put 0, it becomes class 1. If you put 1, then it becomes also class 1, not equal to 0, not equal to class 0. That means there exists no root in Z2 of this f bar x polynomial. Then what would be your conclusion? What would be your conclusion? This is irreducible in where? This is irreducible in where?
Q,
Z2.
In Qx.
QX.
And also, since this is a primitive polynomial, this is also irreducible in Zx. But what was our question? Let us see. So this is rational number. So by using this result, you can say that this is irreducible in Z2 as well as in Q. Now you can very easily say that this is a degree greater than equal to 3. As a result, over R, it can never be irreducible. That means fx must be reducible in Rx. Now we are only left with f3. Let's have a look at this. How will you say about f3? So if I consider f3, f3x, that becomes x cube plus class 2 x square plus x minus 1, that means plus 2 class, that belongs to z3x. Now try to find some elements. What is the value of f0, f1 and f2? Tell me, what is this value of f0? This is class 2. What is the value of f1? This 1 plus 2 plus 1 plus 2. That means class 0. What does it mean? That means x minus class 1 is a root of this polynomial. That means within z3x, this is reducible. Is it clear? So the question was, is it irreducible or reducible within this field? So as you have seen that, if I put 1 here, then it becomes 0, then that means x minus 1 would be a root of this polynomial. As a result, this is reducible. So the answer will be 1 as well as 3. So here you will not be possible to reduce, this is reducible over R, this is also reducible. Is it clear to all of you? Any question?
Sir,
Yes.
sir, we can do this in another way. The first option.
Yes.
If Q is a field, so if there exists a root which is in Q, then
Yes.
it will be of the form A by B.
Yes.
Then
Then
A
it will
divides.
divide this and
Yes.
this, and from there you will also, yes, that can also be done. But since you have to do this problem, from this problem, this option will be automatic, right? From 3, option 1 is automatic, and from Q, this option is not automatic. So for competitive exam, you also have to budget your time. So first look at all the possible options and then try to select which option you should start first. That's also very important. So if you do whatever you did is perfectly okay. But since within the same problem, I also have this, and after solving this problem, I can also give a conclusion for one. So the better choice would be to start with this or this. If you find for this is irreducible, then also you are done. For this, it will also be irreducible. Okay. So you have to be very careful about your time management. That is also very important for any competitive exam. Time management is really very important. But your process is absolutely correct. No doubt about that. Okay. So is it any other queries or questions or comments? Okay. Now tell me this. It came in December 2018. Is it visible?
Yes, sir.
Okay. Right. Anybody?
Sir, option 2 is false.
Why false?
Sir, we can say it with the help of number theory that x to the power 7 minus 105x is always even and 12 is even, so that can't be odd.
Yes, x to the power 7 minus 105x. How you can say that this is even always?
Sir, we are considering two cases when x is even and x is odd. So
Yes.
is if x is even, then x to the power 7 is even, 105x is even, and 12 is even. And
Yes.
if x is odd, then x to the power 7 minus 105x is even, and 12 is even.
Yeah, that you can also take a x common and then you can say then x to the power 6 minus 105. So if it is odd, if it is even, then already done, x is even. And if it x is odd, then x to the power 7 is odd, 105 is odd. That means it's even. That way, yeah. So anyway, this well. So x to the power 7 minus 105x plus 12 is always even. So you can never have this value. That is correct. Then what's about 3, 4, and 1? If you are done with 3, then you are done with 4, right? For 3, suppose there exists some integer m such that this happens. Then have a look at this new polynomial. So fm equal to 2, and then try to think. What's about the first option?
Sir, is
Sir,
it's true.
First option is true or
True.
false? True. Why?
Sir, in Z2 it's reducible and it's
In
primitive
Z2
code.
it's reducible or irreducible?
Reducible.
Yes, if it is reducible, then you cannot say something. The results shows or the result tells only about irreducibility. If it is irreducible, then it is irreducible in the original field or original ring. But if it is reducible, it's not saying anything. But why not you are
Sir,
using this Eigenstein criteria?
yes, sir. I use that, and if x is irreducible over q, yes.
Yes, fx is also irreducible over z. Take prime to be 3. That will be fine. Okay, so the first one is correct. Second one is never be correct because it has to be an even number. Now the question
So
is
first one, sir, the first one is false. If x
false.
is
Yeah, so
irreducible over q.
irreducible. So it has to be by Eigenstein criteria, it has to be irreducible. And here it's given reducible. So the first one is of course false. The second one is also of course false because there exists this fm value will always be even. So 2 can never happen. Now what's about 3 and 4?
So 3 is false, I think.
Okay, why?
Sir, fx is a increasing function for mod x greater than 2.
Mod x greater than 2, it's increasing function. How do you say?
So I have taken the derivative f dash x, and it is 7x to the power 6 minus 105, and it's greater than 0 when mod x greater than 2, the derivative.
Okay, mod x greater than 2. If you put 2, then yes, 2 to the power 7. Yeah.
So now it easily follows. I can check the values and 0, 1, and 2, and 0, minus 1, and minus 2. In 0,
Yes.
it's 12, and if I take 1, it is negative again, and it's 2, it is again negative, and it's 3, and it's a big positive number, and after that, it will increase.
Okay.
Again, I have put minus 1, it is a positive number, minus 2, again a positive number, and it will again increase. After minus 2, minus 3, minus 4, it will increase.
Okay. Then what's about 4? If it is not correct, then 4 has to be correct. I mean, 4, how can it be correct? If m is not a prime number for any integer, okay, then if it is false, then the 4 must be correct, right?
Yes, sir.
So
Sir,
then, yes,
we can do this in another way. We
yeah,
consider gx, which is fx minus 2, and then
yes,
use Eisenstein's criteria again. So
yes. Then what
then
would be?
gx would be irreducible over qx and zx as well.
Yes.
So option 3 is false, and any prime number is either 2 or any the other prime numbers are odd integers. So yeah.
No, then it is irreducible. That's fine. Your gx is irreducible. Then what would, why then fm cannot be equal to 2?
Then
So
we cannot get any integer such that gx is equal to 0, that is fx is equal to 2.
it is irreducible. It is irreducible means what? That's why, I mean, you have correctly said, but give just one extra line.
That means we cannot uh, if any integer is a root of gx, then that would be gx would be reducible, right?
Yes, but yeah, that's true. So no integer. Good. So his argument is like this. Just a minute. He considers a polynomial. Okay, the first point was fx is irreducible over q. It follows from Eisenstein criteria, right? Take p to be 3, and then 3 divides, okay, let me put x to the power 7. Fx is x to the power 7. Can anybody tell me what is next? Minus 105x plus 12 was there, right? So
Yes,
this
sir.
belongs to qx. Okay. Now take p to be 3, then p divides 12, p divides 105, p square does not divide 1, and p square does not divide 12, and p does not divide 1. So then by Eigenstein criteria, this is irreducible in qx. So fx is irreducible in qx. So that's done. The first one is it irreducible, but it says that it is reducible. So first one is false. What's about the second one? Second one is basically you can write the way that Orco-Provo made. Fx equal to, you can write it like this, x to the power 6 minus 105 plus 12. Now x could be either even or odd. If x is even, then this is even, that means this part is even plus even, so fx is even. Now if x is odd, then x to the power 6 is always odd, right? And this is odd minus odd, so that means this is even, so the whole thing is even. Okay, so fx is always even for all x belongs to z. But here it says that fm equal to 105. That cannot happen because for no integer fx will be odd. So here it's given odd, that's why this is also not possible. Now let's come to the third one. It says that fx equal fm, there exists some integer such that fm equal to 2. From this argument, it directly cannot violate, right? It says that if m will be an even integer and 2 is an even integer, so you cannot directly negate from here. Now consider another polynomial gx, which is nothing but fx minus 2. Okay, so how gx looks like? Gx equal to x to the power 7 minus 105x plus 10. This belongs to zx. Now by Eigenstein criteria, you can see that gx is irreducible in qx as well as in zx by Eigenstein criteria. So here p is my 5. That means this is irreducible. So if this is irreducible, then it will be clear that you cannot have a, so this is an odd degree. Okay, now Okopovo, can you please repeat your conclusion?
If there was any integer,
Suppose
say
m
m,
is there, yes,
and gm equals to 0, then gx would be reducible over say.
yes, if there exists any integer m such that gx equal to 0, then your x minus m will be a root of, I mean, will be a factor of gx, right? So that will imply gx is reducible. But just now we have seen that gx is irreducible. So there exists no such m such that gx equal to 0. That is, no such m such that fm equal to 2. Clear? That's why the condition 4 is, what was the condition 4? gm is, so it says that there is exists no such m So 1, 2, 3 are not happening. As a result, automatically 4 will happen. For any integer. Just now we have seen that fm could be, fm must be an even integer. And just now we have excluded this one, that if m can never be 2. That means we have excluded all of them. So if m is not a prime integer for any integer m, that is correct. Is the argument clear to all of you? Any question? Is it clear to all of you? Good. Now have a look at this problem. This one. It came in December 2019 net. It's again, today we have all done this. Can anybody tell me what would be the answer?
Sir, option 1, 2, and 3.
So just now we have seen that if f is a field, then fx is a PID, fx is a UFD. So 1, 2 is correct. Fx is a Euclidean domain. We have also seen that fx is an Euclidean domain. So 2 and 3 we have already seen in our first half of the class, and then we have seen that every PID is again an UFD. So this is also correct, and fx is a PID but not an Euclidean domain. That is not correct. So 1, 2 and 3 are correct. So the information that we had, the theorem that I stated you and I gave the proof to be done at your home, that has to be done. And if you know all those results, then it's very easy. So just now I have mentioned this result, you try to keep in your mind and try to give the counter examples like field implies. Can you repeat? Field implies, what is that? Field implies, anybody?
Sir, ED.
ED.
Euclidean.
Very good. Then
PID.
PID,
PID. Very good. Then
UFD,
EFD. Very good. Then factorization domain, then integral domain, and then commutative ring with one. So this part is very important, and try to always remember the other part is not correct in general, and try to find the counter examples for that. And that will help you lot of things for many of the interviews as well as many of the exams. Okay, let's see what else. Okay, it came in December 2019. Let fx be in zx be a monic polynomial of degree n. Then which of the following are true? Fx is irreducible in zx, then it is irreducible in qx. So it will again be multiple correct choice. More than one could be correct.
Sir, yes, sir. The first option is true.
Okay. So if fx is irreducible in zx, then it is irreducible in qx. It's a monic polynomial of degree n. So what do you mean by monic polynomial? So the monic polynomial is basically a polynomial whose leading coefficient is unity. That means the we can say that with unit maybe. So the monic polynomial is a polynomial of this form. A polynomial, say fx equal to a0 plus a1x plus anx to the power n. This is the leading term of this polynomial, and this has to be unity. Okay, so if this is 1, then you can say that this is a monic polynomial. Or if it is an unit, then you can make it a monic. So you can make a inverse, you can multiply with the inverse of an to have this term an. That means it should generally looks like a0 plus an minus 1 x to the power n minus 1 and so on, a0. So this polynomial is an example of a monic polynomial. So since your fx is a monic polynomial, then if one of the term is 1, so here this you have 1, then of course the GCD with others, it should be a unit. Okay, uh, so that's why this monic polynomial of degree n, then which of the following? So if it is irreducible, so this is a primitive polynomial, then irreducible, then it must be irreducible in qx. So the result is correct. Is it clear to all of you? Okay, what's about the next one? So both of, since if it is a primitive polynomial, then both of them must be correct, right? It's an if and only if. If it is here, then it will be also here. If it is here, then it will also be here. So both 1 and 2 are correct. Then what's about 3? What's about 3 and 4?
So 3 is false, I guess.
Sir, 4 is false.
Okay, 4 is false. Why?
Sir, if we take fx is equal to x square minus 2,
Okay,
so
then
it is
if x has a root, if x has a real root, then it is reducible in x. So as you mentioned, fx equal to x square minus 2. So this is belongs to no doubt zx, but it has no real root, right? I mean, it has real root. It has real root. The roots are plus minus root 2, which does not belongs to z, but suddenly belongs to r. So it has real roots. So fx has real roots, then it is reducible in zx. But as you understand, it's a degree 2 polynomial and it has no root in z, or it has no root in q actually. You should work with q. It has no root in q. As a result, it should be irreducible in q. And since this is a primitive polynomial, it is irreducible in z. So it is irreducible in z. So x square minus 2 is irreducible in z, but it has no real root. So 4 is also false. Now the question is, what is 3?
So 3 is also false.
Example?
X square plus 1 whole square.
Very good. So x square plus 1 whole square has no real root. No doubt about this. But it is reducible. So x square plus 1 whole square is reducible in zx, because you can x square plus 1 into x square plus 1. It says that then it has a real root, but it has no real root. So it is reducible in zx, but it has no real root. So this result is false. So which one is the answer? Which are basically here? So we can see that here option 1 is correct, option 2 is correct, but option 3 and 4 are false. Okay.